All right, today we are diving into a really cool paper that gets at a huge question in AI. Can these models learn genuinely new skills, or are they just, remixing what they've already seen on the internet? Now, the title sounds a bit nerdy, from f of x and g of x to f of g of x, but the idea behind it is actually super simple, and we're going to break it all down. Let's get right into it.
So this is really the core of the whole thing. When we train an AI and see it get better at something, is it actually learning? Or is it just getting better at recognizing patterns from the mountains of data it was trained on? This is, no joke, one of the biggest debates happening in the AI world right now.
And that leads us right into our first section, AI's great debate. Because you've got these two camps, right? On one side, people see these incredible new abilities popping up. But on the other, you have a lot of skeptics who think it's all just a very, very clever illusion.
So let's lay out the two big arguments. The optimistic view is that something like reinforcement learning, or RL, can teach a model brand new skills, like how to reason step by step. But the pessimistic view, which people call the re-ranking argument, says RL doesn't teach anything new at all. It just helps the AI get better at picking from answers it already knows how to generate. Think of it like this. It's not learning to cook a new dish, it's just getting better at picking the right recipe from a cookbook it already has completely memorized.
And this is where things get really tricky for researchers. It's this problem of data contamination. I mean, how can you prove an AI learned something new when it might have just seen a similar problem somewhere in its training data, which is basically the whole internet? It makes running a clean experiment almost impossible. It's like, how do you test a student for new knowledge when they've already read every single book in the library?
So what did the researchers do? Well, their solution was to build their own custom gym, a totally clean, completely controlled laboratory for the AI. This way, they could be 100% sure the model had never, ever seen these tests before.
And here's how they did it, in 3 key steps. First, to avoid that data contamination problem, they created totally new synthetic tasks using string transformations. And they gave them these generic names like Func16, so the AI couldn't just look up the answer. Second, they defined these simple tasks as atomic skills. And finally, they could precisely control the difficulty by combining these functions into more complex, nested problems, like Func15 of Func16 of x. Okay, this brings us to the absolute heart of this paper. It's all about the difference between knowing how to do one simple thing and knowing how to combine a bunch of simple things to do something complex.
So what in the world is an atomic skill? Well, think of it as the most basic building block you can have. It's a single, simple task that can't be broken down any further. It's kind of like learning the letter A. You can't simplify it anymore. It just is A. Here's a perfect, concrete example. An atomic skill could be a simple function that just removes repeating letters from a word. So you give it HEEELLO, and it gives you back HELO. That's it. The model just has to learn that one simple rule.
But a compositional skill, that's a whole different ballgame. It's not about knowing one thing. It's the ability to take multiple atomic skills, multiple letters of the alphabet, let's say, and string them together in just the right order to solve a much bigger problem. It's the difference between knowing your ABCs and actually being able to write a sentence.
So let's take this one step further. What if the AI knows that atomic skill compressed repeats, and it also knows a different atomic skill reverse a string? The real question is, can it figure out how to combine both of those skills to turn hilo into ole? That requires a much, much deeper level of understanding. And that right there is the million-dollar question this whole study is trying to answer. To put it back in those mathy terms, if you teach a model f of x, let's say reverse, and you also teach it g of x, compress repeats, can it figure out, all on its own, how to solve for f of g of x? Can it tackle a combined problem it has never seen before?
All right, time to get to the results. And the paper calls this a breakout performance, which is a pretty cool way to frame it. This is where we see the actual evidence.
And the results here are, wow, they are just so clear. When the AI was only trained on those simple single atomic skills, its accuracy on a really hard 3-step problem was basically 0, around 1%. But, and this is the kicker, when it was trained on intermediate 2-step problems, its accuracy on those much harder 3-step problems skyrocketed to almost 30%. That is a huge leap, and it's really the key finding of this entire paper.
So here's the crucial takeaway from that graph. The model didn't just get a little bit better at something it could already do. No, it learned a fundamentally new thing. The ability to combine skills is, in and of itself, a brand new skill.
And honestly, it gets even crazier. This new meta skill of being able to combine things was transferable. Get this, the model learned how to combine these weird string functions, right? But that general ability helped it solve a completely different kind of problem, math puzzles from the game show Countdown. The only catch was, it had to already know the basic atomic math skills like addition and subtraction to begin with. And with that evidence, the paper pretty confidently says that this result completely shatters the re-ranking illusion, that pessimistic idea that the AI is just reshuffling old tricks. No, this looks like a genuinely new trick.
So you might be wondering, why did people even have this re-ranking illusion in the first place? Well, it all comes down to how hard the problem is. On easy problems, the basic AI already has a little bit of success, so reinforcement learning just gives it a small boost. But on hard problems, where the base model is totally clueless, RL is forced to build that compositional skill from the ground up, and that creates this huge performance gap you see in the data. So the skeptics, it seems, were just looking at problems that were too easy.
The researchers also dug into the types of mistakes the AI was making, which is super interesting. Before training, its mistakes were fundamental, like it would completely miss a step or get the order totally wrong. But after training, the main type of error changed. The AI now understood the overall plan, the composition, but it would make a small mistake on one of the basic steps. This shows it actually learned how to approach the problem correctly, even if it sometimes messed up the tiny details.
Okay, so all of this is incredibly cool from a research standpoint, but what does it actually mean? Why does this matter for the future of AI? What are the big takeaways here? Well, the paper's own conclusion really says it best. They suggest a totally new strategy for building AI. Instead of just trying to make models bigger and bigger, we should focus on building base models that have a really strong foundation of different basic skills, and then use reinforcement learning to specifically teach them how to combine those skills.
So this basically gives us a simple two-step recipe for building smarter AI. Step 1, you build a solid foundation. You teach the model a whole bunch of different atomic skills, the alphabet, so to speak. And then step 2, you use reinforcement learning with more complex, compositional problems to teach it how to write poetry, how to combine those basic skills in new, interesting, and powerful ways.
And that leaves us with one final, kind of mind-bending thought to chew on. This research proves that AI can learn how to combine skills that we give it. But what's the next step? What happens when an AI learns how to invent its own atomic skills, and then starts composing those? That's a question for the future for sure. But thanks to work like this, it feels like that future might be just a little bit closer.
Hey everyone, and welcome back. So we're diving into a huge question in AI today. You know when a model gets way better at something? Is it actually learning, like a new skill? Or is it just getting really, really good at faking it? Let's dig in. Yeah, this really gets to the core of it, right? We see these AIs doing amazing things, and it's easy to be impressed. But there's this nagging debate. Is it actually coming up with new stuff? Or is it just a super clever parrot, just rearranging all the things it's already seen on the internet? Real learning or just an incredible illusion? All right, so here's how we're going to break this down. First, we'll look at the big debate itself. Then, we'll see how some researchers set up a really smart test to get some real answers. We'll find out what the key to learning actually is and whether that new skill can travel. We'll also bust a pretty common myth and then wrap up with what this all means for AI. Okay, first up, the great AI debate. So it all kind of boils down to this one training method called reinforcement learning, or RL for short. It's super powerful, for sure. But the big question, the real mystery, is can RL actually teach a language model a brand new skill, something from scratch that it didn't know before? So you've basically got two camps here. On one side, people are like, come on, look at the results. RL is obviously teaching these things new tricks. But then the other side pushes back, saying, hold on a minute. This model has seen like the entire internet. Maybe RL isn't teaching it anything new, it's just making it better at finding and reusing the best strategies it already picked up from all that data. So how do you even test this? You can't just throw a problem from the internet at it because the AI might have already seen the answer, right? It's contaminated. No, you need a totally clean scientific setup. And that is exactly what these researchers did. They built this really clever testbed to get a clean answer once and for all. And their method was brilliant. It had three main parts. First, to make sure the AI couldn't cheat, they created brand new puzzles using totally meaningless names, like Funk 16. So there's no way it had seen them before. Then, they taught the model really simple single-step skills. Think of them as basic building blocks. They called these atomic skills. And then came the real test. Could the AI take those simple blocks and combine them on its own to solve way more complex, multi-step puzzles?
Let's make this super clear. An atomic skill is like knowing how to do one simple thing. You see f of x, you know what to do. Easy. But a compositional skill, that's the magic. That's looking at a problem you've never seen before, like gf of x, and realizing, oh, I need to do f of x first, and then take that result and plug it into g. It's not just doing a task, it's understanding the process of how to combine tasks. That's a whole different ballgame.
Okay, so the stage is set. We have this perfect, clean experiment. So what happened? What did they find? What was the secret sauce that actually made the AI learn something new? And this is the big aha moment right here. Just using RL on those simple one-step problems, it did basically nothing. The real breakthrough, the key, was using RL on the compositional problems, the ones that forced the model to combine steps. So it wasn't just the training method, it was the method plus the right kind of problem. And this chart just lays it all out perfectly. Check this out. When they tested it on the really hard three-step puzzles, look at that first bar. Standard training, basically just showing it examples, it got a measly 2.6%. The second bar, using RL on just the simple skills, even worse, less than 1%. But then look at that third bar. After training with RL on the compositional problems, its performance on the hard stuff jumped all the way to 30%. That is a huge leap. So what does that tell us? The researchers' takeaway was super clear. The AI wasn't just memorizing answers. It was learning the actual logic of how to combine things. It learned the idea of composition. And that is a brand new skill. Okay, awesome. The AI learned a genuinely new skill. But is that skill stuck in this one little puzzle world? Or can it actually take that knowledge and apply it somewhere completely different? You know, can the skill travel? And honestly, the answer here is kind of mind-blowing. It's a massive yes. This might be the most amazing part of the whole study. That skill it learned on those word puzzles, it transferred over to a totally different task, a math puzzle called Countdown. And get this, the model had never been trained on complex multi-step countdown problems, but the skill just worked. The proof is right in these numbers. The basic model, the one that only knew the simple math rules, it could solve the countdown puzzle about 17% of the time. Not bad. But the model that had already learned compositional reasoning from the other puzzle, it more than doubled its score, hitting 35%. That's huge. It proves this isn't just a skill for one specific task. It's a meta skill, a skill about how to solve problems in general. Now, this isn't just magic. There's a key condition. For this to work, the model still needs to learn the basic building blocks for the new task first. So for the countdown game, it had to be taught basic arithmetic. But once it had those atomic skills, that meta skill of composition that it learned before just kicked right in and told it how to put those new blocks together way more effectively. So this brings us full circle, right back to that initial debate. Remember the argument that RL is just re-ranking what the AI already knows? Well, this research suggests that's not the whole story. The researchers even have a name for it, the re-ranking illusion. And this is so cool, it shows why people thought it was just re-ranking. See, if you only look at the easy problems, the argument kind of holds up. The gap between the models gets smaller if you give them more tries. But look what happens with the hard problems. The opposite. The performance gap between the smart model and the base model gets wider the more you look. That's the smoking gun right there. It proves the trained model has a skill the base model literally just does not possess, period. So let's step back. We've gone through all this data. What does it all mean? What's the big picture here for AI? Okay, let's nail down the key takeaways. 1. RL can teach an AI a genuinely new skill as long as you train it on the right stuff. 2. That stuff has to be compositional problems that force it to combine simple things. 3. This new skill can actually transfer to totally different areas. 4. That whole re-ranking idea is basically an illusion you see when the problems are too easy. And 5, this really changes how we should think about training the next generation of AI. And if you remember just one thing from all this, make it this number, 30%. That's the performance jump on tough problems that the model was getting close to 0 on before. That isn't just a little boost. That's a new skill being born. right there in the data. So that leaves us with a pretty wild thought to end on. We've seen solid proof that an AI can learn how to learn, how to combine simple building blocks into something more complex, all on its own. So what new abilities is it going to compose next?
All right, so let's get right into it. Have you ever stopped and wondered if an AI is actually learning new things, or is it just getting really, really good at shuffling around what it already knows? I mean, it's one of the biggest questions, one of the biggest debates happening in AI right now. Well, today, we're going to dive into some absolutely fascinating research where scientists basically built a custom playground for an AI, all to figure out if it can genuinely learn a new skill, and that skill is the art of combination. Okay, so this is the real heart of the issue. The big question is, when we use a technique like reinforcement learning to train an AI, are we actually teaching it something brand new, something fundamentally different? Or are we just helping it get smarter at using the knowledge it already picked up during its first big training run? Just shuffling things around, reprioritizing. The truth is, researchers are totally split on this. And the answer? Well, it gets to the very core of what we think AI is even capable of.
So you've basically got two camps, two competing ideas here. In one corner, you have the genuine learning folks. They believe that reinforcement learning, or RL for short, can give an AI totally new abilities, the kind of skills that let it solve problems it has never, ever seen before. But then, in the other corner, you've got the re-ranking theory. The idea here is that RL is really just a fancy filter. It looks at all the reasoning patterns the AI already has, finds the best ones, and just turns up the volume on them. So in this view, it's not really learning anything new, it's just getting way better at using what it already knows.
Okay, so how do you even begin to settle a debate like this? Well, here's the problem. You can't just throw problems from the internet at the AI. Why? Because it might have already seen them during its training. It could just be remembering the answer. So to get around that, these researchers did something really smart. They built what they called a clean room, a totally synthetic, completely controlled environment designed for one purpose: to find out how an AI really learns, with no cheating.
And their setup was honestly pretty brilliant in its simplicity. It came down to 3 key steps. First up, decontamination. They created brand new puzzles from scratch. These were string transformation tasks, think reversing a word or something, but they used totally abstract names for them, like Funk16. This made sure the AI had absolutely zero prior exposure. It was starting from a clean slate. Second, they separated the tasks really clearly into simple problems and complex ones. And third, and this is the clever part, they came up with a way to precisely control the difficulty by nesting these simple functions together, one inside the other.
So to understand what they found, we need to get a handle on 2 key terms. The first is an atomic skill. Think of this as the absolute most basic building block of knowledge. It's a single, fundamental ability that you can't break down any further. The analogy they use is perfect. It's like a musician learning to play a single note, just one. In their experiment, this was the AI learning how to solve one of those simple string functions. Let's call it f of x.
Okay, so if an atomic skill is a single note, what comes next? Well, that's a compositional skill. And this is where it gets interesting. This is the ability to combine those individual atomic skills to tackle something more complex. So instead of just playing one note, now you're playing a whole melody. You're putting the notes together in the right order. From a math perspective, the question becomes, if the AI knows how to do f of x and it knows how to do g of x, can it figure out how to do g of f of x all by itself without anyone ever showing it that specific combination? This is the new skill they were hunting for.
All right, so the stage is set, the clean room is built, and the experiments are running. And what the researchers found? Well, it was a genuine breakthrough. They pinpointed the one key ingredient the AI needed to finally unlock this powerful new skill of combination.
And this really brings us to the core of the whole experiment, the million-dollar question. What happens if you train an AI on some simple 2-step combinations and then you test it on much harder 3-step, maybe even 4-step combinations that it has absolutely never seen before? Can it make that leap? Can it generalize?
Well, the answer's right here, and the results were absolutely striking. Take the AI that was only trained on those basic single-step atomic skills. When faced with a hard, unseen problem, it was basically useless, a 1% success rate. But the AI that was trained on just simple 2-step compositions, suddenly it could solve 30% of the much harder 3-step problems. I mean, that's a 30-fold jump in performance. This wasn't just memorization. It was clear the AI had learned a general principle. You know, the researchers themselves put it best in their paper. The big takeaway is that using reinforcement learning on this kind of compositional data actually teaches the AI a brand new skill. a skill it can then generalize to solve new, more complex compositions it's never encountered. This is a huge piece of evidence for that genuine learning side of the debate.
But here's a crucial detail. It wasn't just what the AI trained on, it was how it was trained. See, they tried a much simpler training method, something called rejection sampling fine-tuning, or RFF. You can think of this as just showing the AI a huge list of correct answers. And guess what? It totally failed. It couldn't learn the general skill. It was the specific process of reinforcement learning, that whole trial and error feedback loop, where it gets rewarded for trying the right things. That was the secret sauce. That was essential for the breakthrough.
Okay, so the AI can combine skills. That's a big deal. But a skeptic would immediately jump in and say, hold on a second. It hasn't learned a new skill, it's just gotten better at finding an answer it could have found anyway if you just gave it enough guesses. Well, the next part of this research takes that exact argument head on.
And they have a name for this counterargument: the re-ranking illusion. The idea is that reinforcement learning doesn't actually expand the AI's toolbox. It just makes the AI better and faster at picking the right tool for the job on its first try. It doesn't actually give it any new tools. But the question is that really what's going on here?
This chart right here is basically the nail in the coffin for that simple re-ranking theory. It's showing something called pass at K, which is just a fancy way of saying what's the probability of getting the right answer if you get K attempts. Now, on easy problems, the re-ranking idea kind of holds up. If you give both models enough guesses, the gap between them shrinks. But look at what happens on the hard problems. It's the complete opposite. The more attempts you give them, the wider the performance gap gets. This means the RL-trained model is solving problems the base model simply cannot solve, no matter how many chances it gets. It has unlocked a totally new capability.
So, if we dig into why the basic models were failing, the picture becomes really clear. This analysis shows that a whopping 85% of the time, they either ignored the fact that it was a combination problem altogether, or they just tried to combine the skills in the wrong way. Bottom line, they just fundamentally did not understand the task.
But now, check out the failure analysis for the model trained with reinforcement learning. It's a completely different story. First off, it's actually solving almost 30% of the problems correctly. And when it does fail, the number one reason is something they call an atomic error. This is such a critical insight. It means the AI gets the big picture. It understands the high-level plan for how to combine the skills, but it sometimes just messes up on one of the simple steps. It's exactly like a musician who knows the melody perfectly but accidentally hits one wrong note. This is massive proof that it really did learn the new high-level skill of composition.
And look, this isn't just some interesting academic exercise. What they discovered here really points toward a clearer, maybe even more efficient path for building much smarter, much more capable AI systems down the road. This is where things get really powerful. It turns out this ability to combine skills isn't just stuck in the world of string puzzles. The researchers found that it's a transferable meta-skill. Think of it as a skill about how to use other skills. And because of that, the AI can take this new ability and apply it to completely different kinds of problems.
And the proof is right here in this table. It's pretty amazing. So they tested the AI on a totally new task, a math puzzle called Countdown. The first model, the one that only knew the basic string puzzle skills, well, obviously, it failed completely. No surprise there. Then they took a model that knew the basic math skills for the Countdown puzzle, but hadn't learned the composition skill. It struggled. But then, look at this last row. They took a model that knew the basic math skills and had already learned the composition meta skill from the string puzzles. The result? A huge performance boost, hitting 35% accuracy. The meta skill literally transferred from language to math.
So, what does this all boil down to? It means we might have a whole new strategy for developing AI. Step 1. Build base models that have a really strong, diverse foundation of these atomic skills. Give them a huge vocabulary of basic abilities. Step 2. Use reinforcement learning with these kinds of compositional tasks to teach the AI the all-important meta-skill of how to combine them. You know, this could be a much smarter, much more efficient path to building truly intelligent systems, instead of just making the models bigger and bigger and bigger.
And all of this leaves us with a really provocative question to think about. As we're all racing to build more and more powerful AI, maybe the answer isn't just about massive scale. Maybe the real path forward is about teaching our models something more fundamental. Maybe it's about teaching them the very human skill of how to take old ideas and combine them to create something completely new.